Hello everyone, welcome to our low temperature thermochronology online lectures. Today we'll be learning Chapter 5, Fission track thermochronology, especially its theory background. In this chapter, we have 5 sections including fission track formation, fission track age calculation, track length analysis, fission track annealing, and presentation and modeling of fission track data. Now, let's start with Section 1, Fission track formation. In the late 1950s, using transmission electron microscopy, TEM for short, it was discovered that heavy charged particles passing through insulating materials can leave trails of radiation damage. Soon afterwards, damage trails were demonstrated to be fixed and enlarged by a simple process of chemical etching, which made them visible under an ordinary microscope. This discovery led to the development of fission track, or FT for short, dating. Track formed over geological time by spontaneous fission of uranium-238 were first observed in natural micas by Press and Walker in 1962. And in 1963, these two physicians firstly proposed that fission track could be used as a geological dating method. Since then, fission track dating has become a robust dating tool that has become successfully applied in various disciplines of geosciences. The fission track dating method is based on spontaneous fission decay of a parent isotope uranium-238 and analysis of the accumulation of physical damage to the crystal lattice resulting from the fission process. On geological timescales, the spontaneous fission of uranium-238 is the major reaction accounting for the accumulation of fission tracks. The half-lives of all other naturally occurring heavy isotopes such as uranium-235 and thorium-232 that undergo spontaneous fission are too long to produce a significant number of tracks. Only about 1 in 2 million uranium-238 decay event occurs from spontaneous fission decay. Each fission event produces a single straight fission track when the two fragments formed by the subequal halves of the original 238 nuclei fly apart in opposite direction, leaving behind a continuous up to 20 microns long linear defect, as is illustrated by the animation. High-resolution TEM images of nuclear tracks show that the core of fission track is approximately 10 nanometers in diameter and consists of a region of amorphous material that has untransitioned to a normal undamaged crystal lattice. The amorphous material is essentially glass that is much more chemical reactive than the surrounding undamaged lattice. This property is critically important as it provides the possibility of distinguishing latent tracks from the host mineral using chemical etching. Each fossil fission track represents a single uranium-238 nucleus that has undergone a spontaneous fission. So counting the number of spontaneous tracks in a mineral grain gives a quantitative measure of daughter products of fission events. Here is a cartoon representation of the ion spike explosion model and the formation of fission tracks in a mineral. In Part A here, trace amounts of radioactive uranium-238 are present in the crystal lattice, as is shown in the dark circles here. And we can see that this inherently unstable as a result of the atomic structure of uranium-238. In Part B, spontaneous fission of uranium-238 produces two highly charged heavy particles and releases about 200 million electron voltage of energy. This frequency of fission event is low, about 1 for every 200,000 of alpha particle decay events. The masses of the two highly charged particles generally differ, with mass number in the range from 85 to 105 and about 130 to 150. The highly charged particles recoil and interact with other atoms in the lattice, initially by electron stripping or ionization. This leads to further deformation of the lattice as the ionized lattice atoms repel each other. In part C, it shows that the fission particles capture electrons. They slow down and begin to interact by atomic collisions, further reducing the particles' energy until they come to rest, leaving a damaged trail or fission track. This cannot be observed optically unless chemical etched. The effect of spontaneous fission on lattice deformation is vividly expressed in this cartoon here. The original lattice starts to be deformed as fission track will be formed. Given that fission tracks could be readily observed optically under high magnification, and that fission process occurs at a constant rate, it soon became apparent that fission tracks provided a practical method of dating materials. The major difference between fission track dating and other conventional isotope dating method is that the daughter product is physical damage to the crystal lattice, rather than other isotopes. In order to be useful as a dating method, there needs to be a sufficient concentration of the parent, for example, uranium-238, to produce a detectable number of fission events. On the other hand, too high a concentration of uranium-238 can result in so much fission-induced damage that it's not possible to distinguish individual tracks. Fortunately, the appropriate range in concentration for accumulation over geological timescales, about 1 to 1,000 ppm, is typical of relatively common minerals such as apatite, zircon, and titanite. The number of tracks in an apatite grain depends on 1. Uranium content, and 2. Time. Therefore, in principle, if we measure the uranium content and the number of tracks, we can measure the time over which tracks have accumulated, which is the fission track age. But if we measure fission track ages in subsurface samples, we will find that at temperatures greater than about 70 degrees centigrade, the ages are progressively reduced to zero at around 120 degrees centigrade. Fission track annealing will be discussed in detail later in section 5.4. The above is section 1. Thank you.